Think of nanorobots as incredibly tiny machines, much smaller than a human cell, that can perform specific tasks inside our bodies or in other complex environments. Nanorobots are incredibly important because they hold the potential to revolutionize many aspects of our lives, from medicine and technology to environmental protection, perform surgeries at the leading to quicker recovery times and less pain. Early disease detection. These tiny robots could continuously monitor your body for signs of disease, detecting issues like cancer or infections much earlier than current methods, which means treatments can start sooner and be more effective. 2. Advancing technology, precision. Manufacturing. In the tech world, nanorobots can assemble components at an atomic level, leading to the creation of stronger, lighter, and more efficient materials and products. Think about how much more advanced our electronics could become with these precise manufacturing capabilities. Repair and maintenance. In the future, nanorobots could be used to repair small defects in materials or machinery, extending their lifespan and performance. This could be crucial for maintaining critical infrastructure without the need for large-scale repairs. 3. Environmental protection pollution cleanup. Nanorobots could help clean up environmental pollutants, such as breaking down oil spills or removing microplastics from oceans. This could significantly improve the health of our planet's ecosystems. Water purification. They could also be used to purify water, making it safe to drink by removing contaminants at a molecular level, which could be especially valuable in areas lacking clean water. 4. Synergy with AI, enhanced capabilities. With AI, nanorobots can become even more effective. AI can help them navigate complex environments, make real-time decisions, and coordinate their actions. This synergy means that nanorobots can perform tasks more intelligently and efficiently, pushing the boundaries of what's possible. While the current state of nanorobotics does not yet allow for the creation of fully functional nanorobots, AI-driven animations and simulations provide valuable tools for visualizing and understanding the potential of this technology. These visual representations help bridge the gap between theoretical research and public perception, fostering greater interest and support for ongoing scientific efforts. Media and popular science often amplify the potential of nanorobots, creating unrealistic expectations about their current capabilities and timelines for breakthroughs. Stories and movies featuring nanorobots performing miraculous tasks can distort public perception, leading to an overestimation of what is scientifically feasible in the near term. The intricate challenges involved in developing functional nanorobots, such as quantum mechanical limitations, material science issues, and energy supply, are often understated or overlooked in mainstream discussions. While biological cells function as natural nanorobots, replicating their complexity synthetically is immensely challenging. The intricate biochemical processes and self-repair mechanisms in cells are difficult to duplicate with current nanotechnology. Let's explore the scientific principles behind the tiny machines that promise to change medicine and technology. In 1986, Eric Drexler built on Richard Feynman's ideas in his book, Engines of Creation. Drexler introduced the world to molecular nanotechnology, envisioning nanomachines and assemblers that could build complex structures atom by atom. But why aren't humans and other organisms the size of nanorobots? The answer lies in the mix of biological, physical, and environmental factors shaped by millions of years of evolution. First, there's the surface area to volume ratio. As an organism increases in size, this ratio decreases. Smaller organisms have a higher surface area relative to their volume, making processes like diffusion efficient, but also leading to rapid loss of heat and water. Second, the complexity of multicellular life. Maintaining complex bodily functions at the nanoscale is nearly impossible. Specialized cells and systems like the circulatory and nervous systems require a certain minimum size to function effectively. For example, neurons need a specific length to transmit signals. Third, metabolic requirements. Larger organisms can store more energy and use it more efficiently over time. Very small organisms have high metabolic rates and energy requirements that might be unsustainable. Larger bodies also support more complex behaviors and higher cognitive functions, which are energetically expensive. Fourth, environmental interactions. Organisms interact with their environment based on their size. At the nanoscale, forces like viscosity dominate over inertia, fundamentally altering movement and other functions. Nanoscopic organisms face vastly different survival strategies and environmental niches compared to larger ones. Fifth, evolutionary pressures and adaptations. Evolution favors traits that enhance an organism's fitness in its environment. Larger size can be advantageous for capturing prey, avoiding predators, and thermoregulation. Very small sizes might limit these functions. Sixth, structural and functional constraints. Biological materials like proteins and nucleic acids have properties optimized for certain size ranges. Constructing fully functional organisms at the nanoscale would require overcoming these material constraints. Seventh, reproduction and development. Processes like reproduction and development benefit from a specific size range. Smaller organisms might face challenges in reproductive processes that require intricate structures and interactions. While significant progress has been made in nanotechnology and molecular electronics, creating intelligent nanorobots at the true molecular level faces big challenges. Despite their potential, nanorobots remain largely in the realm of science fiction. Quantum mechanical limitations. At the nanoscale, quantum tunneling becomes a significant issue. Electrons can pass through barriers, making it difficult to create reliable and stable electronic components. Maintaining quantum coherence, where particles remain in a superposition state, is challenging due to environmental interactions causing decoherence. Thermal energy at the nanoscale causes random motion, making precise control difficult. As devices shrink, their surface area to volume ratio increases, leading to significant challenges in managing heat. Nanorobots could easily overheat, causing failure of delicate components. Van der Waals forces cause nanoparticles to stick to each other and surfaces, leading to aggregation. Surface tension, stronger at smaller scales, can hinder movement and operation in fluids. Conventional materials may not work the same way when miniaturized. Manufacturing techniques lack the precision to produce complex nanoscale components reliably. Energy supply and efficiency. Finding a sustainable and efficient power source is challenging. The energy density required to perform complex tasks is difficult to achieve without generating excessive heat. Control and communication. Effective communication is challenging due to signal propagation limitations. Implementing advanced AI algorithms in small form factors is currently beyond reach. Biocompatibility and safety. Nanorobots must be biocompatible to avoid triggering immune responses. Ensuring safe degradation or removal from the body is essential. Nanorobots must often operate in a fluidic state to avoid immobilization and aggregation due to van der Waals forces and covalent bonding. In a fluid environment, nanorobots benefit from reduced friction and enhanced mobility. Brownian motion can aid passive transport, though controlling movement remains a challenge. Operating in a fluidic state helps nanorobots avoid sticking and aggregation, as particles are more easily separated and dispersed. Surface modifications like hydrophilic or hydrophobic coatings further reduce the likelihood of sticking. Fluidic environments also facilitate dynamic interactions, such as self-assembly and disassembly. Nanorobots can adapt more readily to environmental changes, enhancing their ability to perform complex tasks. However, despite the exciting possibilities, the current state of nanorobotics is hindered by fundamental physical and technological challenges. Quantum mechanical limitations, thermal fluctuations, surface forces, material properties, energy supply, control and communication issues, and biocompatibility concerns all present significant barriers to the development of functional, intelligent nanorobots. While research continues to make incremental advancements, the vision of autonomous, intelligent nanorobots remains a distant goal, firmly rooted in the realm of science fiction for now. The direction of nanorobotics, though promising in theoretical research, must overcome these substantial hurdles before it can become a practical reality. Philosophically, the pursuit of nanorobots represents humanity's innate drive to push beyond natural limits and enhance our capabilities through technology. This endeavor parallels the evolution of artificial intelligence and digital technology, which aim to augment human intellect and physical abilities. As we delve deeper into the quantum world, we uncover the fundamental principles that govern the behavior of matter at the smallest scales, opening new avenues for technological innovation. The exploration of nanorobotics challenges our understanding of life, intelligence, and the boundaries of human ingenuity. AI can profoundly enhance the capabilities of nanorobots, making them smarter, more efficient, and more effective. By integrating AI, nanorobots can autonomously navigate complex environments, make real-time decisions, and work collaboratively, opening up new possibilities in medicine, manufacturing, environmental cleanup, and beyond. This synergy between AI and nanotechnology represents a significant step towards realizing the full potential of nanorobots. Thank you for joining us on this exploration of the untold story of nanorobots. Stay tuned for more insights into the fascinating world of nanotechnology.